Yeah, who knows? All right. So hello again. I'm Jerry Xuan. I'm a graduate student at Caltech. Um, and yeah, I'll be talking about how I keep trying to study planets, but always finding brown dwarfs, which are also cool. And this is in the context of KPIC. So let's just so I use the neutral term substellar companions here to encompass the whole population of objects that have been uncovered with direct imaging over the years. These objects typically uh, are more massive than Jupiter, and they span all the way to the hydrogen burning limit. Their occurrence rate is pretty low, but it does vary a bit. So surveys have looked at hundreds of stars and tried to quantify the occurrence rate of these objects as well as other things. So if you try to fit the occurrence of these objects as a function of their mass, orbital semi-major axis, the stellar mass they orbit, and things like this, you find that, okay, so first let's just have a definition of giant planets. Let's say they're below the nominal deuterium burning limit of 13 Jupiter masses, and brown dwarfs are those above. Then there are actually observable differences. What we call giant planets have orbit closer to their stars, and they actually have a higher occurrence rate that's closer to the RV giant occurrence rate measured, for example, by the California Planet Search Team. And giant planets also tend to exist around higher mass stars. Furthermore, people have looked at the orbital architectures of these systems and found possible differences in this population. So one result that came out is looking at the eccentricities of these objects, and the finding is that giant planets are more circular than their brown dwarf counterparts. There's recent work that shows that this is sensitive to the prior choices because these orbits are obviously they're not on human timescales. These are tens to hundreds of AU orbits. But a similar distinction is still seen in these recent papers. The other thing you can do is to measure stellar obliquities, so similar to how you do it for hot Jupiters. But in this case, what people do is they try to measure the orbital axis of the orbit and then the stellar spin axis just from V sin I and the rotation period of star. And there might be possible trends there, but more work needs to be done. In summary, though, previous work has shown that there might be an emerging picture over the past few years that objects with higher masses, typically above 10 or 15 or so, it's a fuzzy boundary, and typically at wider separations might be essentially brown dwarf companions that form as the tail end of star formation via direct gravitational collapse. On the other hand, for those 1 to 10 Jupiter mass objects, we're really not sure, but they could be consistent with the core accretion and runaway gas accretion theory, which happens in a protoplanetary disk and happens on a much longer time scale. So there's an empirical question that we're trying to answer as part of the KPIC science goals, which is, do we see a similar difference if we measure the elemental abundances of these objects? So if we actually measure the amount of carbon and oxygen in their atmospheres and compare to the stellar values, their host star values, do we see that the more massive objects look more like their stars, which is observed for stellar binaries? And do we see more different possibilities, possible differences between the compositions of the planets and the stars for the lower mass objects, which can depend on many different factors. So doing this in the context of KPIC, which is at Keck 2, and so we're that weird instrument that uses the NERC2 light path, but uses NIRSPEC as a science detector. So I'd like to thank all the Keck OAs and SAs for supporting KPIC and tolerating us. So essentially KPIC, as I said, is taking the light from the Keck 2 AO system and channeling it through single mode fibers into near spec. We use near spec in the high resolution mode with R of about 35,000, typically in the K band. And one of the advantages of this is that our fibers are actually on the order of 50 milliarc seconds in diameter. So they couple in basically no sky background and much less speckle background from the bright stars that we're trying to observe companions around. And KPIC has been successfully running for a few years now. And we've detected a lot of different companions. There's a whole nother hot Jupiter survey that Luke Finnerty is going to talk about in a bit. But these are just the widely separated substellar companions. And in this talk, I'm actually going to focus on a subsample, which is these intermediate mass objects, which are above, more planet-like things, but less massive than the high mass brown dwarfs, some of which we actually have dynamical masses for. So these are all photometric masses. And many science papers have came out over the years on the sample and the hot Jupiter sample as well. And I think there's almost 6 more science papers to be submitted in the next 6 months or so. So, but this is the sample I'm going to talk about today. And essentially, I take the high-resolution spectra from NearSpec, and I fit it with a forward model, which accounts for any possible leakage from the starlight and a bunch of other things. To generate the companion model, I use radiative transfer code to compute the spectra on the fly. So a new spectra is computed at each step of the fit. And this has benefited from new opacity data, from new line lists. So I'm using these new line lists and converting them into opacities that better describe the molecules we're probing. And finally, everything is fitted in a nested sampling framework where I'm mostly interested in the abundances for this work. So we parameterize this usually as the overall carbon abundance and this carbon over oxygen ratio. And I'll talk about isotopic ratios in a bit. So for now, I'm going to compare everything to the sun, but I'll talk about the stars later. The 8 companions that I've looked at so far, most of them are really in line with the solar C to O ratio, which is shown in the blue shaded area. And they're color-coded, these points are color-coded by mass ratio. So everything looks pretty solar. We can also measure the carbon abundance. So this is now shown in the y-axis, and the x-axis is C to O ratio. The contours in color are 1 sigma contours of the retrieved abundances, and the solar value is shown in the gray oval. So here I'm going to make a leap of faith and say that currently what we're going to assume is that the young stars, which all of these are, in many of the same star-forming regions as our objects are known to have solar metallicities as well as solar abundances for a range of other elements, including alpha process elements. And so right now we're assuming that carbon and oxygen, which are also alpha process elements of the host stars, are probably also solar. So right now we don't yet have the host star abundances to compare with, but we're making this assumption right now. And that would be the subject of future work. But if this is true, then these companions are indeed chemically similar to their host stars. So in a sense, what I'm saying is the stellar people need to give us more abundances. But it is a challenging problem for young stars, obviously. Another thing that is been, it's a bit, but it basically this says isotope log ratios are a new observable for these objects. So the first isotope log ratio was measured of 2 years ago. This was the ratio between 12CO, which is the most abundant form of carbon monoxide, and 13CO. It is really not clear, I would say, what this tells us, but it's just something that's quite easy to measure in the K-band. So people have started doing this. There are some ideas that this ratio changes in the disk, but more modeling needs to be done to actually show this. We do measure this in a lot of our K-pick data, and in this sample of 8, there's 3 that have a bounded isotope log ratio constraint. So these are the red squares. The other 2 squares are also from K-pick for other objects. And here I'm plotting it against mass ratio. So the higher mass ratio things are more like binary stars. I also overplotted the solar value and the value for the local ISM. So I wouldn't interpret this plot too much, but it's really just to show you that we can now measure this, and we have K-pick spectra in the K-band of many of these, of all these host stars as well. So a lot of the host stars have low enough temperatures that CO lines are seen in the K-band. So we can also do a similar measurement in the future. But to summarize, I'm currently studying this sample of intermediate mass objects. Not sure what they are, but at the moment they look like the sun, and if we assume their stars are also of solar composition, then they look like they're stars. So this means these objects are probably consistent with a star-like formation pathway, which is what previous studies have also been hinting at. And in the future, we're going to try to measure the C and O abundances in the host stars as well. So yeah, thanks.